We do it 100 times a day. We send messages, watch videos, load websites, and it all happens in the blink of an eye. It kind of feels like magic, right? Well, it's not. And in this explainer, we're going to pull back the curtain on the incredible, super intricate system that makes it all possible. I mean, really think about it for a second. You type a website into your browser, you hit enter, and bam, a page from a server maybe halfway across the planet just appears on your screen. So what actually happens in those few seconds? What's the invisible journey your request takes? That's the mystery we're going to solve today. So the way we're going to do this is to frame it as a story. Think of it like an epic quest. We're going to follow just one single piece of your data as it travels from your screen all the way across the globe and back again, just to load one simple web page. And every good quest needs a map. And this is ours. It's called the Internet Protocol Suite. Now, don't let all the technical terms scare you off. Just think of these different layers as, different territories our little piece of data has to cross. It starts right at the top, travels all the way down just to leave your computer, and then it does the entire trip in reverse when it finally gets to where it's going. All right, so let's follow that single request on its journey. We're going to start at the very top of our map in what's called the application layer. This is the part where you, the user, kick the whole thing off. Okay, so the very first step is actually a lot like wanting to call a friend, right? Before you can actually talk to them, you have to know their phone number. The internet, believe it or not, works pretty much the exact same way. See, your computer doesn't understand example.com, but it totally understands numbers. And that's where the domain name system, or DNS, comes into play. You can think of it as the internet's phone book. Its whole job is to translate the name you can read into a numerical IP address that the computer can actually use to find the server. And this is a really crucial two-step process. First, your browser asks a DNS server, hey, what's the number for example.com? The DNS server shoots back the IP address, and only then can your browser send its actual request for the website's content to that new address. So what is that request exactly? Well, it's a message written in a very specific language called HTTP, which stands for Hypertext Transfer Protocol. The best way to think about it is like a set of rules for having a conversation on the web. Your computer sends an HTTP GET request, which is basically its way of saying, hey, please give me the content of this web page. Okay, so we've got our message, and we know where it's going, but how does it actually get there? Well, let's move down our map to the next couple of layers, where the internet's very own postal service takes over. First things first, you can't just mail, say, a whole novel in one giant envelope, right? It's way too big. You'd have to send it page by page. Well, the internet does the exact same thing. Your request and the web page you get back, they're both broken down into thousands of tiny little pieces called packets. But if you're mailing a novel as a bunch of separate postcards, how do you make sure they all get there and that they're put back in the right order? Well, that's the job of something called TCP, the Transmission Control Protocol. What it does is it numbers each packet, each postcard, so they can be put back together correctly. And it checks to make sure that none of them get lost along the way. And this is such a brilliant way to see how TCP makes sure everything is reliable. After sending a packet, it just waits. It waits for a little acknowledgement message to come back, kind of like a thumbs up, confirming it was received. And if it doesn't get that confirmation, it just sends the packet again. Simple as that. No data gets left behind. Now, of course, for our postcards to actually get delivered, each one needs an address. And that's the job of IP, the Internet Protocol. You see, every single device on the internet has its own unique IP address. So what IP does is it stamps each and every packet with the to address of the server and the from address of your computer. And get this journey is not a direct flight. Not at all. It's actually a frantic series of hops. Your little packet travels from your computer to your local router, and then it just bounces between dozens of other routers all across the internet. Each one looks at the address and forwards the packet along what it thinks is the most efficient path at that precise moment. So the really crucial point here is that these protocols don't work in isolation. They're all designed to work together in what's called a stack, where each layer adds its own set of instructions to the packet. A good way to think about it is like preparing a package to mail. Your HTTP request, that's the letter you put inside. Then TCP comes along and wraps it in paper, numbering it for delivery. And then, finally, IP puts that whole wrapped package into a mailing box and slaps the address on the outside. Each layer basically wraps up the one above it. Okay, but what if you're sending sensitive information like your credit card number? Well, for a secure HTTPS site, we just add one more layer to the stack. Simple. Before TCP wraps up the message, a protocol called TLS, that's Transport Layer Security, it locks your data in an encrypted box so that nobody can read it on its journey. See? Security is really just another layer.
So, all of this globe-spanning, lightning-fast, and honestly remarkably reliable system, it all works because of one single powerful idea. Let's take a look at what makes it all possible.
Just imagine for a second that one computer sends a message that represents the word hi, but the computer on the other end is expecting a number, so it interprets that exact same message as 18,537. Total confusion, right? Communication fails. The solution's pretty simple, though. Both computers have to agree on the rules beforehand, and this agreement, that's a standard. And here is the most crucial part of this whole thing. The internet's rules are open standards. What that means is that everyone uses the same playbook. But, and this is key, the rules are open. They aren't owned by any single company. Anyone, anywhere in the world, can read them, build new software with them, and connect to this global network without asking anyone for permission. You know, this wasn't some happy accident. It was the entire point from the very beginning. As Vint Cerf, who's one of the fathers of the internet, said, the whole theory was to create a system that could just grow organically, with no central control. And by making the rules open, they basically invited the entire world to come and build it together. And that's exactly what happened. So the next time you hit enter, just take a second to remember what's happening behind the scenes. It's not magic. It's actually something way more impressive. A monumental, ongoing achievement in global cooperation, all built on a shared set of rules that allow every one of us to connect and communicate. This incredible foundation of open agreement has allowed the internet to grow and evolve for decades. And it kind of leaves us with a final thought. As our digital world keeps changing so fast, what new rules might we need to make sure it stays open and beneficial for everyone? What do you think?